Hey everybody, so we're going to continue our discussion of complex numbers, and what we're looking at now is integer powers and roots. So we're going to start with examining what happens with integer powers, right? So exponents that are going to be whole numbers, and actually in this case positive whole numbers. So I've written down a couple of complex numbers here, z and w. I've written them in three forms, right? A plus bi for z, c plus di for w in the rectangular form, and then I can write them both in polar and exponential, right? Using our conversion techniques, we could find the radius and the angle for each of them, and so I have each in this r cosine theta plus I sine theta form, or r e to the I theta, okay? So let's just look at what happens when we multiply. Let's remind ourselves. Recall that if we multiply z times w, and I'm going to look at the polar and exponential forms this time, we get, remember, we end up just multiplying their radii together and adding the angles. Right? That was in one of our previous videos. We showed through the sum formula for sine and cosine, that when we multiply two together, this is what we get. We've simply added the two angles and multiplied the radii. So what if you multiply a complex number by itself? Well, then you're multiplying the radii by itself, and you're adding the same angle to itself. All right, and if we simplify this, so on this left-hand side, we see that this is z squared. And over here, we're going to get r1 squared, and we get cosine of 2 theta 1 plus I sine of 2 theta 1, right? And we can write this in its exponential form, right? Just like up here, this could be written as r1, r2, e to the I theta 1 plus theta 2. Here we're going to get r1 squared, e to the I 2 theta 1. Okay, so notice what's happened. We've squared it, we square the radius, and we get twice the angle. Well, you can imagine if we multiplied by z again, we would now cube z. We would have to cube the radii, and we'd add in another copy of theta 1, which would give us 3 theta 1. And so what happens in general is every time we multiply by z again, which is what our positive integer exponents does for us, right? Cubed is just 3 factors of z, 18th to the 18th power is just 18 factors of z. We will take that radius to the same power, and we'll multiply the angle by that number. Okay. Same thing in our exponential form. Okay, and so this gives us a really nice way to expand powers of these complex numbers. So let's do it with a real number, well, a complex number, but an actual example instead of abstractions. So if I take w equals 1 plus I, let's compute w to the 4th. Now, one thing we could always do, right, is actually multiply this out. Right, to the 4th power just means 4 factors of this. So we'll get, if we multiply, we get 1 times 1 is 1. We'll get plus I plus another I. But then I times I is I squared, which is minus 1. That's the first two. The second two are going to look exactly the same. And so we end up with, sorry, I lost my train of thought there. We've got a 1 and a -1, so we've just got 2i. And then the same thing here, so we've got 2i, so we've got 2 times 2 is 4, and we've got I squared, so we end up with -4. Right, so that wasn't horrible, but imagine if this was the 12th power or the 5th power or something like that. Alternatively, we can convert this into polar form. It's pretty quick to see. Well, let's just write it out. R is going to be the square root of 1 squared plus 1 squared, or the root of 2. And theta is going to be the tangent inverse of 1, y over x. They're both 1 here. It's in the first quadrant, so we don't need to add pi. And we get pi over 4. So this is equal to root 2 cosine pi over 4 plus I sine of pi over 4, which means, using our new formula, w to the 4th, oh, let's do the polar as well, so root 2 e to the I pi over 4. The 4th power of this, well, we'll get root 2 to the 4th. Cosine, we're multiplying the angle by 4, so pi over 4 times 4 is just pi. Root 2 to the 4th, e to the I pi. Root 2 to the 4th is simply 4, so we get 4 cosine of pi plus I sine pi, or 4 e to the I pi. All right, and notice if you multiply this out, cosine of pi is -1, sine of pi is 0, so it's just a -1 times 4, which agrees with what we got up above. So it gives us an alternative way to compute these. And again, if you're multiplying, or if you're taking a very high power, right, to the 5th, to the 9th, to the 12th power, this method of just simply multiplying becomes tremendously easier than having to expand this rectangular form over and over and over again. Okay, let's do another one, but first let's also mention this gives us a nice geometric interpretation, right? What's happening when we're taking a number? So when we look at our abstract formula here, when we take z to the n power, we get the radius to the n power, and we're multiplying the angle. The radius to the nth power, and we're multiplying the angle. So we start with a complex number that's right, it lives somewhere on our complex plane. All right, so maybe here's my number, there's its radius, there's theta. Taking r to a power changes its length, right? And so if it's bigger than 1, taking it to powers will make it grow. If it's smaller than 1, taking it to integer powers will make it shrink. So the radius will change length, right, depending on what size it is. So the radius will either expand or contract. And at the same time, multiplying the angle is going to rotate it around, right? If you start with theta here, if you square it, you get to 2 theta, right? You get another copy of theta. And so your point rotates around, and then the radius grows or expands, right? So you'll get something like, maybe if that radius is expanding, it'll rotate around and end up somewhere up there. We'll look at this again with a nicer graphing program than my sketches, but it is a nice way to interpret the powers that isn't really obvious when we look at it in this form. So we get this nice geometric interpretation. But we'll come back to that. Let's look at a couple of other examples. Something interesting shows up. So let's consider a number z equals, and I'm going to stick with polar form, an exponential form, 2 cosine of 2 pi over 3 plus I sine of 2 pi over 3, also written as 2e to the I 2 pi over 3. Okay, let's cube this number. Pretty straightforward. Z cubed is going to be equal to 2 cubed cosine 2 pi over 3 times 3 is just 2 pi plus I sine of 2 pi equals 2 cubed e to the I 2 pi, right? And I can write this as 8 cosine of 2 pi plus I sine of 2 pi equals 8 e to the I 2 pi. Now let's notice something about this number. Cosine of 2 pi is 1, right? We've gone all the way around the unit circle back to where we started. Sine of 2 pi is 0. So this whole part in the parentheses is simply 1, and we've got an 8, and this applies to both of them. This whole thing is just the real number 8, right? This is a complex number where its imaginary part is 0. What that means is that this complex number, z, must be the cube root of 8, right? That's what a cube root is. It's a number that when you cube it, if I ask for the cube root of x, I'm looking for a number that when I cube it, I get x. So here's a number that when we cube it, we get 8. That must be the cube root of 8, right? But we know the cube root of 8. The cube root of 8 is 2, and this number up here is not 2, right? Cosine of 2 pi over 3 and sine of 2 pi over 3 are not 0, are not 1 and 0, and so this has a real and imaginary part. It's different than 2, and it's not 2, right? Doesn't mean 2 is not also a cube root of 8, because it's definitely true that 2 cubed is 8. We just did that when we were computing this number. So what's going on here? Well, let's do a couple things. First, let's write 8 or 2 as a complex number in polar form. So the way I can write this is as cosine of 0 plus I sine of 0, or 2e to the I 0. This is kind of a weird way to write this. If we have a 0 up there, it seems strange to leave it, but I'm just pointing something out. So notice this is the number 2. Cosine of 0 is 1, sine of 0 is 0. So this is really just 2 times 1, but we're writing it in complex polar form, okay? If we cube it, of course, we cube 2 to get 8. We have cosine of 0 times 3, which is still 0, plus I sine of 0. We get 8e to the I. 0 times 3, still 0. I times 0 is still 0. I'm just writing it to kind of reinforce that it's in, we're talking about complex numbers. And so, in fact, we do get that 2 is the cube root of 8 as well, right? Because this number here is 8. Cosine of 0 is 1, sine of 0 is 0. So this is 8 times 1, right? So it turns out there's at least one more cube root of 8 that we never knew about, okay? And in fact, we will find out that that's not the only one, but we're going to put this on pause for a moment and talk about roots. So let's start fresh, okay? So let's just remind ourselves, I already mentioned this, but let's remind ourselves of a few things. A cube root, right? If we have, let's say, the square root of x, right? Which can also be written as x to the 1/2. This is a number that when squared gives us x, right? Or more generally, if we have the nth root of x, which we can also write as 1 over an exponent of 1 over n, this is a number that when we take it to the nth power, we get x, right? So the 4th root of 16 is equal to 2, because 2 to the 4th is equal to 16, right? So this is what cube roots are, right? So let's examine what happens when we look for roots, nth roots of complex numbers. So let's start with the complex number z. We'll let z be r e to the I theta, or r cosine theta plus I sine of theta. But I'm gonna use the exponential form for this little examination. This is what's nice about having these forms. You can use they're all equivalent. They're equivalent to each other. And so if you discover something true about one of them, it's true about all of them. So let's do this. Let's see. Let's say that we want, oops, where's my eraser? There we go. Let's say we want the nth root of z. So that's going to be some complex number, right? I'll just call it w, where w to the n equals z, right? This is what has to be true. So w is a complex number, which means we can write it as, I'll call it s e to the I alpha, right? It's some radius. I'm using s because we already used r, e to the I alpha, right? Which we could, of course, write as s cosine alpha plus I sine alpha, okay? So we want that w to the n equals z. Well, w to the n will be s to the n, e to the I, n times alpha, right? That's just our power. That's the rule we discovered about powers. This has to be equal to r e to the I theta, right? Because we know that w to the n is equal to z. That's the number, that's the only thing we know about w, is that when we take it to the nth power, it's equal to z. So let's look at this equation in the middle here, right? So what I'm saying is the number, whatever a complex number s to the n e to the I n theta is, it's the same complex number as r e to the I theta. So if two complex numbers are the same, if we put them into the complex plane, they must be in the same place, which means their radii have to be the same. In other words, s to the n is equal to r. And the angle must be the same. N alpha has to be equal to theta, right? This is the alpha for w to the n. Sorry, this is the angle for w to the n, and this is the angle for z. So those two angles have to be the same. Okay. Now, this first equation, these are just two real numbers, right? 5 cubed equals r, or whatever these numbers are, right? So if remember, we're starting with z. We have z and we want to find its nth root. So we'll know r, and we're looking for a number that when taken to the nth power gives us r. Well, that's what we call the nth root. So given a number r, we take the nth root of r to get the radius of the new complex number that's going to be the nth root of our complex number, okay? So if the radius of z is 8, and we're finding the cube root, we know the radius has to be 2, the cube root of 8. Let's look now at the n alpha part, okay? So n alpha has to equal theta, the angle for z, right? But we've also seen that the way we express things in polar coordinates isn't unique. You can have plus 2 pi, or plus 4 pi, or plus 8 pi, or plus 10 pi, right? As long as that's a full rotation, some full multiple rotation. So we write that, remember, as 2 pi times k, where k is an integer. Okay, so we have these multiple possible roots. Well, let's solve this equation for alpha. Alpha is going to be equal to theta over n plus 2 pi k over n. Okay, so we're getting an infinite number of solutions here, okay, that we want to write down for the angle that we need for this complex number, the nth root of z. So we have everything we need right now, right? We've got the new radii, new radius, and we've got at least an expression for alpha that gives us the set of all solutions. However, this set of infinite solutions repeats. So what we're going to do is write down kind of the principal solutions. And so let's examine what I mean by that. Let's look at this graphically for a second. So let's throw a unit circle in here. So whatever theta is, some angle, theta divided by n will be some other angle. So let's just call this theta over n, right? I'm just representing this. We don't know how big it actually is. So this is when k equals 0. So I'm going to write out here theta over n plus 2 pi over n times 0, right? So this is this 2 pi, we're doing theta over n plus 2 pi over n times k. I just put that k off to the side to make it a little easier to see. Then when k is equal to 1, we get the next, we're going to add a little piece, 2 pi. Well, let's just write it. So now I have, this is going to be theta, I'm going to write out here, theta over n. Sorry, there's just going to be no space. Oh, sorry, I got to switch this. There we go. Okay. All right, theta over n plus 2 pi over n times 1. So that means that this little piece just from here to here is 2 pi over n, right? We've added one of those pieces to theta over n. So this bigger angle here, that's theta over n plus 2 pi over n, and this is a little 2 pi over n. So now I want to keep adding pieces of this size, right? Here's another 2 pi over n, which makes this bigger angle theta over n plus 2 pi over n times 2. Okay, so we're going to keep adding pieces like this. Well, what happens when we add n of those pieces? Whatever n is, what happens when we add n of them? We get theta over n plus 2 pi over n times n, right? When I add one piece, when I add no pieces, there's a 0 there. When I add one piece, there's a 1 there. Two pieces, there's a 2 there. At some point, I'll have added n pieces, right? If it's the 5th root, n would be 5 after 5 pieces. The 50th root after 50 pieces, n is equal to 50. These n's cancel, and we get theta over n plus 2 pi. So after we add n of those pieces, we land right back where we started, right? This angle here is just theta over n plus 2 pi. I'm going to write it as 2 pi n over n, because that's what we were doing. We added n pieces, but of course that cancels, so we get back to where we started. So what happened, and then as we continue to let k grow, remember these are the values of k, we're going to add another piece, we're going to land on this one again, and then we'll add another piece and land here again, and all the pieces that go all the way around. So after we get all the way back around to where we started, we just keep listing the same numbers, the same complex numbers in different ways over and over again. And we don't want to do that. We want to just write down these principal roots, these first n roots, starting with the one where k is 0. We want to end not when we get back to where we started, but the one before, right? There'll be one right here where we haven't added in the last piece to get to 2 pi. So what we'll do, we'll say k is going to be equal, instead of an integer, it's going to be 0, 1, 2, up to, if we stopped at n, we'd be listing this first complex number twice, so we'll stop right before that. And this will give us a list of all the roots of this number, right? Without doubling down and writing them in all the different ways we can express them in the polar coordinates. And so there are n roots here, right? So if n is equal to 10, you'll have 0 through 9, but remember there's 1, 2, 3, 4, 5, 6, 7, 8, 9 of them here, and then the 0th root is our 10th. So when we stop at n minus 1, we're still getting n roots because we're starting at 0, not at 1. Okay, and this gives us our solutions. The roots are going to be a set of numbers with r to the 1 over, oops, let's write this a little differently. Let's write this as z to the 1 over n z to the 1 over n is r to the n e to the I times theta over n plus 2 pi k over n, where k is equal to 0, 1, 2, up to n minus 1. Okay, it's a little bit complicated, but we'll do an example in just a second. In fact, let's do an example right now. Let's look at the number that started all this confusion. Let's take a look at the complex number 8. All right, so I'm thinking of it as 8 plus 0i. It's a complex number, but the imaginary part is 0. We can write this in polar form as 8 cosine of 0 plus I sine of 0, or 8 e to the I times 0. Okay, so this is our z. All right, it's just the number 8 written in a complicated way. Well, let's find the cube root of z, and I'm going to use this formula. Z to the 1/3 is equal to, well, we take the 1/3 power of the radius, so 8 to the 1/3, and then we're going to have e to the I 0. Let's write it this way. 0 over 3 plus 2 pi k over 3, where k is equal to 0, 1, and 2, right? So n is 3 here. N is, remember, the root we're finding, so we stop 1 before that. And these are the numbers. Let's write them out explicitly, though. So I'm gonna give these a name. I'm gonna call W0 the first root, when k is equal to 0. So we're gonna get 8 to the 1/3 is 2, e to the I. When k is 0, this term is gone, and we just have a 0 here, right? So this is just the number 2. E to the I 0 times 0 is just 2. This is the complex number 2, where the imaginary part is 0. So this is the root we're used to. But it turns out there's 2 other cube roots. 2e to the I 0 over 3 plus 2 pi over 3 times 1. This is when k equals 1, so I'm putting a 1 in here for k. I can simplify this as W1, I already have W1, is 2 e to the I 2 pi over 3. Okay, and we have one more. So this is the one we found earlier. All right, these are the 2 we found earlier, right? We found that when we cubed 2e to the I 2 pi over 3, we got 8. And then we also we recognized that 2 is also the cube root. And it turns out there's a third. This is going to be 2e to the I 0 over 3 plus 2 pi over 3 times 2, which is 2e to the I 4 pi over 3. And these are the 3 cube roots of 8, right? We didn't know there were 3 before. Right? We've always thought of the cube root of 8 as being 2, but now we find out there's 3 numbers. It just happens to be that 2 of them are complex, right? So it's similar to maybe before you knew about negative numbers, you knew that there was a square root of 4 is 2, but then it turns out there's 2 square roots, -2 and 2. Well, it turns out that whatever root we're taking, the 3rd root, the 5th root, the 19th root, there's that many roots of that number, right? So here we took the cube root, we found 3 cube roots. Let's look at a picture of this. So these numbers all live. So instead of this being a unit circle, this is going to be a circle with radius 2. Right? And there's our first cube root of 8. the second cube root also has radius 2, so it's on this circle, but it's at an angle of 2 pi over 3, which is about right here. So this is W1, this is W, oops, sorry, this is W naught, W1, and then 4 pi over 3 is down here, right? Notice these are the pieces I was talking about adding, right? My picture's not perfect, but we have an angle of 2 pi over 3. We get another angle of 2 pi over 3 and another angle of 2 pi over 3. And so we split the circle, this radius 2 circle, into 3 even portions by angle. And that gives us the location of our three roots, okay? So it's a nice little geometric interpretation, right? If there were 18 roots, we'd be chopping this circle into 18 even pieces and spreading out around that, starting from wherever the first root was. All right, let's do one more example, and then we'll look at a prettier graph than the one I've drawn here. All right, so let's start with a more interesting number than 8. Let's look at a complex number, -2 plus 2 root 3 I. And we want to find z to the 1/4. Okay. So I'm going to start by changing this to exponential, right? This is a much more difficult problem to solve without having a polar or exponential. So first, I need the radius, or the modulus, of z. So that's -2 squared plus 2 root 3 squared. What do we get? We get 4 plus 12, or 16. The square root of 16 is 4. So the radius is 4. Theta we can find by taking the tangent inverse of y over x. So 2 root 3 over -2 is going to be -√3. Okay, sorry, there's a small error on my notes, but this is correct what I've written here. Let's see, this is a point in the -2 root 3. This is in quadrant 2, where we have to add pi to our answer. So the inverse tangent of this is -pi over 3. We're adding pi to it. We get 2 pi over 3. So we're getting the complex number in polar form. Looks like 4 cosine of 2 pi over 3 plus I sine of 2 pi over 3, or in exponential form, 4e to the I 2 pi over 3. Okay, so there is our number. Let's compute z to the 1/4. Okay, so we need 2 pieces, the new radius and the new angles. So the radius is straightforward. We take the old radius and we take it to the 1/4 power. So this is the 4th root of 4. There's really not a better way to write this down. Exactly. I mean, there's a few different forms. We could write a decimal approximation, but I don't like doing that. It also might be nice to notice that this is, right, using the rules of exponents, these would multiply. This is the 4 to the 1/2 power. The square root of 4 is 2. So this is also just 2, the square root of 2. And if you like radicals, you can write it as in this way, right? Same thing. Really, any of these are appropriate for this number. 4 to the 1/4 is a good way to write this number down too. The angle that I like to call alpha, well, it's going to be 2 pi over 3. That's the original angle divided by 4 plus 2 pi over 4. All right, so I'm just using our connection that the radius goes to the nth root of the radius, and then theta leads us to theta over n plus 2 pi k over n. So I forgot to write my k there. And in this case, k is going to be equal to 0, 1, 2, and 3, right? There are 4 fourth roots. So let's write down those fourth roots. We get alpha is equal to 2 pi over 3. This is ugly. Let's fix this up before we do this. So 2 pi over 3 divided by 4 is 2 pi over 12, or pi over 6 plus, and this is just pi over 2 times k. Okay, that's just a little bit easier. So now for these 4, oh yeah, I should be indexing this with k for these 4 roots. So that means alpha 0, when k is equal to 0, is just pi over 6. Alpha 1 is pi over 6 plus pi over 2, which gives us 2 pi over 3. Alpha 2 is pi over 6 plus 2 times pi over 2. So pi over 6 plus pi gives me 7 pi over 6. And alpha 3 is pi over 6 plus 3 halves pi, which you can work out the fractions as 5 pi over 3, right? It might be nice to write these as, this is pi over 6, 4 pi over 6, 7 pi over 6, and 10 pi over 6, right? Because what's happening at each step, we're adding 3 pi over 6, adding 3 pi over 6, adding 3 pi over 6, right? That pi over 2. So each time we increase k, we get another pi over 2. And we're just, if we're starting with 6, I'm just adding 3 pi over 6. So we can visualize this moving around the circle, right? We have these 4 locations. Oops, let's make this nicer. So we have 4 answers, 4 roots. The first one being at pi over 6, right? And this is in a radius of circle, a circle of radius root 2. And then we just keep adding pi over 2, right? A quarter turn around the circle. So these should be at right angles to each other. So the next one should be over there. The next one should be over there. And the next one should be over there, right? We just keep adding pi over 2. And once we do that 4 times, right? So we do it 3 times, because we start with this number, we add one, we get here, add one, we get here, add one, we get here, and we stop, because if we added it again, we get back to where we started, okay? So this gives us our 4 roots. Let's just write them out explicitly. I'll label them with W, so W naught will be root 2 e to the I pi over 6. W1 will be root 2 e to the I 2 pi over 3. W2 is root 2 e to the I, where are we at, 7 pi over 6. And W3 is root 2 e to the I 5 pi over 3. Okay, the last thing we're going to do, right? So each of these numbers, complex numbers, if we take it to the 4th power, like W0 to the 4th is root 2 to the 4th e to the I pi over 6 times 4. Root 2 to the 4th gives me 4. Pi over 6 times 4 is 2 pi over 3, right? So we get back to the number, the z that we started with, right? And you can do that for each of them. But let's think about what taking it to the 4th power does, right? Earlier in the video, I talked about how you can think of it as it changes, it scales the radius, because in this case, it's going to make it bigger because you're taking a number bigger than 1. Square root of 2 is about 1.4, and you keep multiplying by itself. Each time it gets a little bigger. So when we take this number, W naught, which is located right here, and take it to the 4th power, we stretch it out so that its radius is out to 4, right? It should be a little further, but I'm out of space. At the same time, we're going to rotate it, because each time we take it to another integer power, we're multiplying that angle pi over 6 by more and more and more. We end up multiplying it by 4, so we get 4 little copies of this, which actually ends us up over here, except 8 units out. So this point will travel like this, right? For larger angles, each time we multiply, they're adding a larger angle. So they're going to actually rotate even more. So let's look at one last thing before we go. This is the most important thing is just knowing how to compute these numbers, right? We have this nice formula. My formula, here we go, where we take the nth root of the radius, and then we have these this theta over n plus 2 pi k over n, right, for k equals 0 through n minus 1, right? So there's a lot going on there, but it's just plug and play, right? Given the numbers, you can just compute these. But there's a nice interpretation about rotation. So here are these 4 numbers. Here is, this is z. This is what I called W0, W1, W2, W3. I can put them on a circle. Let's add the circle in here. Oops. There we go. So there's a circle with radius √2. Now what I'm going to do with my slider is I can increase the exponent. Right now they all have an exponent of 1 on them. Let's move that exponent to 2. You can see what's happening to all of them. They're being rotated and their radii are getting larger. So here we're at an exponent of 2.01. I couldn't quite stop. Notice they've all traveled different amounts. The one that's started at W0, that was the green one, hasn't moved very far, right? That's that pi over 6 has now moved an extra pi over 6. The one that started at 2 pi over 3 has now moved an extra 2 pi over 3. The one that started at 7 pi over 6 has moved an extra 7 pi over 6. And the one that started at 5 pi over 3 has now moved an extra 5 pi over 3. If we add another exponent, so let's go from 2 to 3, they continue to rotate. Can't quite stop at 3. And get further out, their radii are expanding. And when we continue all the way to 4, we know they're all the 4th root of z, so they all land right on z. Okay, so this is a nice geometric way to see this. Here's our complex numbers sitting around this circle. These are the 4 roots of this number z, the 4 4th roots. And as I increase the exponents, we can see what's happening geometrically to these numbers. They're spiraling, they're rotating around the circle, and their radii are increasing. They all rotate at different speeds, but they all land exactly on z when we get to the 4th power, right? Which is just confirming what we did if you multiply these or take these to the 4th power, you'll see that they all get you to z. Okay, that is it for this one. Thanks, everybody. I will see you next time.